think we stopped at producing an isometric subspace of a metric space which has larger metric dimension. And this example is known to many people. Proof is elementary. I'm sorry to display it in this non-full screen way because I want to see the time underneath as well. The proof we have done, then that example was part of Lei's PhD thesis as well. And this next result is from paper by Bearden and myself from 2013, I guess. The work done before that. And we did, the next natural question was, if we were considering geometric spaces, what is the next natural spaces if we knew already the classical geometric spaces have dimension just one larger than the Lebesgue dimension, then what is the next natural objects metric spaces that we should consider? And it was very natural that the next natural ones are Riemann surfaces. Riemann surfaces are domain of definition of complex valued function with one complex variable. And there is a classification theorem called uniformization theorem, which we utilize. And there is a comment here, which my co-author, Professor Bearden, would be very happy to mention every time. To do undergraduate or honors complex one variable function theory, the best way to do is, of course, there are 5 different ways of doing it. Now it's very interesting to mention. Originally, it was analytic way done by Cauchy and Riemann. And there's also topological approach, which does the elementary basic topology first, and then you do the complex variables, one complex variable through topology. And then there's a linear algebraic way of doing it. So it's already 3 of them I've mentioned. There's also a geometric way of doing it, which is basically going through a hyperbolic metric. And it is very beautiful if you only utilize hyperbolic metric to complex one variable complex function theory. There is a 5th way, which is very recent. In 21st century, some people do it using combinatorics. Precisely speaking, it is using circle packing. And then you have a finitely many circles and circle packing, and then you consider mappings from one packing of circles to another packing of circles, and then you do one variable complex function theory very easily, and you have beautiful illustrations through computer graphics, because for finite circle packing, computers are very suitable for that. So there are at least 5 major ways of treating theory of one complex variable. And among these, the geometric ways to go through Riemann, the hyperbolic metric, which we have already used in the geometric spaces part. And we have a isometric mapping between the 2 metric spaces. One is the complex plane and the other is a hyperbolic plane. And the uniformization theorem was proved. This is a theorem, major theorem in theory of one complex variable, complex valued function of functions of one complex variable, proved during 20th century, not more than 100 years ago. And this theorem is very beautiful. And this theorem completely resolves what Riemann surfaces are like. So let S be any Riemann surface. Then one of the following three is true. Number one is that S is the complex plane, or a cylinder, or a torus as a quotient space of the Euclidean plane by the action of a discrete group of isometries. Secondly, S is the Riemann sphere. In this case, you have only a trivial discrete group action to which, with which the quotient is Riemann sphere. The group consists of only identity mapping, which is, of course, isometry. These two are very easy to visualize. And the last one is, and these two actually are trivial because there are a very small number of such Riemann surfaces here. And the last is, now here we have a group which is infinitely many, which has infinitely many elements. You have a group of isometry of the hyperbolic plane, and then you quotient. Every group action gives you a quotient topological space, which is called D space by the topologist. And this quotient space is equal to the Riemann surface. Here we have infinitely many examples. So every Riemann surface is one of these three types, three major categorical types, but there are subtypes. For example, in the first case, there are many as well. And this we're not going to prove. This was proved in, many people tend to think that, oh, one complex variable is completely done. There's nothing to do. One real variable, real functions are all done, nothing to do. And many university lecturers give this wrong idea to their applied mathematics students. This means that there is nothing much to do in pure mathematics as far as analysis is concerned, but actually this theorem was proved in the late 20th century, 1960 something. New results have been obtained in these old classical fields of mathematics. And we are going to use this theorem to determine, I don't know why people pronounce determine as determine, which is wrong, wrong to me anyway. Determine the dimension of Riemann surfaces. And I'm going to give you the simple idea for the hyperbolic plane, the third type of Riemann surface. We proved that the metric dimension of every Riemann surface is 3, which is quite natural because the Lebesgue dimension of every Riemann surface is 2. And the metric dimension is in the geometric spaces case. In the case of geometric spaces, metric dimension is 1 larger than the dimension. So let us consider a unit open disk. And with G, the Fuchsian group. Fuchsian group is a discrete group of isometries of the hyperbolic plane. And we are using the Poincaré model of open unit disk on which the straight lines are semicircles perpendicular to the boundary. Boundary is not included, as you can see. Let rho be the hyperbolic metricon. And therefore, our Riemann surface is actually a quotient of this disk by G, by the uniformization theorem. And there is a quotient map from D to the quotient. Of course, this is the topological quotient map. If you have a quotient group, this is the surjective mapping, which maps every point of the space D to the equivalence class, even by the group action. and use use x, y for the points in D and x asterisk, y asterisk for the points in the quotient. Don't get confused. I get confused of this sometimes myself. And if the quotient maps x to the x asterisk 1 in the quotient space, then we call x the lift. In topology, so lift, then you're mapping it down and lift it up. And you call x the cover of x star. There might be many points because the group actually is discrete, so there will be finitely many points above x which cover x. The hyperbolic distance in our Riemann surface is denoted by rho asterisk. Riemann surface is the quotient, by the way. That S is the hyperbolic plane. And if these two are points on our Riemann surface, then their hyperbolic distance is given by the distance in the hyperbolic plane between x and y, such that the quotient maps x to x star and y to y star. Then we need to note these following, we need to prove the following two items. One is that the first item is that there exist 3 points on the Riemann surface which resolve the Riemann surface. So the 3-point set, every point from every point on the Riemann surface has a distance. Every 2 distinct points has a different distance to these 3. At least one distance is different. Secondly, we need to prove that no 2 points can resolve. This Professor Muhammad Imran and his colleagues use this all the time because this is 3 points can resolve and then no 2 points can resolve. Then we prove that the dimension is 3. So this first item says that the dimension is at most 3. So let us take any 2 points. Yes, any 2 points UV on the Riemann surface S, which are distinct. 2 means distinct. Then consider the lift. Lift is the pre-image, inverse image under the quotient mapping. And denote the inverse image of U star by U and that of V star by V. These are in D, subsets of D. And we know that these are finite subsets. So for every U in the inverse image and every V in the inverse image of V, let LUV be the hyperbolic geodesic through U and V in D, because D is the model for hyperbolic, for the hyperbolic plane. On the hyperbolic plane, 2 distinct points, just like Euclidean axiom for Euclidean plane, 2 distinct points determine a unique sort of straight line, which is now hyperbolic geodesic through it. And we denote by LUV this hyperbolic geodesic passing through U and V. And this is the countable union of hyperbolic geodesics in D. I said something wrong earlier. Not finite. It's at most countable, countably infinite. And I regard finite sets as countable, different from all my colleagues in the world. So always got into this mistake of calling it finite. Hence, there exists a W in the open unit disk, such that because the D is uncountable, and this set L is countable, this union. Therefore, there must be some point which is not in L, but that is in D. And we take the image under the quotient map Q of W, and that is W star. Then these 3 points dissolve the Riemann surface S. And we are going to prove it. Proof is elementary. This proof is elementary. After the uniformization theorem, these are elementary proofs. Uniformization theorem is not quite elementary. So let us take any point from the Riemann surface, and we want to consider these 3 distances. Distances from UVW to Z star, all star. Let Z be a lift of Z star. And U of U star, V of V star, and W of W star, which is probably not used. Then there are maps F, G, and H in the covering group G. These are elements of the group, such that these groups are maps of the hyperbolic plane, by the way, because it's a Fuchsian group, such that the distances on the Riemann surface is realized even by the distances on the hyperbolic plane or the unit, open unit disk in this way. Because distances are defined, as we have just seen earlier, by means of the minimum of the minimum. This is actually infimum, but infimum is realized in this case, so it's a minimum. We know that these do not lie in the same hyperbolic geodesy, because W was taken to be outside L. And the hyperbolic plane, according to our theorem for geometric spaces, hyperbolic plane is resolved by these 3 points. Therefore, these 3 distances are, these 3 points resolved. I'm not just reading the slides. So we proved that the metric dimension of every Riemann surface is at most 3. Now we prove that it is at least 3. So we will just have to prove that for any 2 given points on the Riemann surface cannot resolve the Riemann surface. For anyone, this is in the hyperbolic case, 3rd case. This is not a complete proof. We didn't do the Euclidean and the Riemann. This is just a demonstration of this for the hyperbolic case. So let us take any 2 points. And suppose that these 2 points resolve the Riemann surface. Let U be the lift of U star, and then DU be the closed Dirichlet region centered at T. This is defined in one complex variable. Then this Dirichlet region is defined by all those points in D such that the distance from U to Z is most the distance from U to GZ. G is the orbit of point Z under the action of the Fuchsian group G. So we're looking at actually an equivalence class here of Z. Oh, sorry, this is U here, sorry. This is a mistype. Distance from U to the equivalence class of G, that is a set. It's a closed set. Dirichlet regions are convex, hyperbolic regions. So in the hyperbolic plane, convexity is defined by, probably you haven't seen this kind of convexity already in Professor Yuan's lectures. Because now convexity is defined by, if you have any 2 distinct points, any 2 points in the hyperbolic plane, then every point of a geodesic hyperbolic arc connecting those 2 is in the set. Then we call this convex set in the hyperbolic, and this is a hyperbolic polygon. And the action of the Fuchsian group is a well-known result in complex analysis that it tessellates the hyperbolic plane, whose model is the unit disk at the moment. Tessellates means it's a cover of the whole plane. Now select one lift of a point V star in this EU. Then V is uniquely determined if it lies in the interior of the EU, but not necessarily uniquely determined if it lies on the boundary of the EU, because the EU set tessellates the plane. EU is convex. The hyperbolic segment is completely inside. This hyperbolic segment is completely inside the Dirichlet region. And U is in dV, so that the UV is also in dV. This means that the whole segment is contained in the intersection of the two Dirichlet region of U and the Dirichlet region of V. So we take the hyperbolic midpoint of UV. UV is, remember, it's a hyperbolic geodesic from connecting U and V. We take the midpoint. Then there exists an open hyperbolic disk centered at W and lies in the intersection of the interior of this intersection. And we take two distinct points in that open neighborhood. Then the hyperbolic bisector of A and B passes through U and B, and therefore you cannot really, it has at least 2 points. It cannot resolve. So we proved that no 2 points can resolve any Riemann surface, and there exist 3 points. We constructed it algorithmically. They resolve the Riemann surface. So we proved that the metric dimension of Riemann surface, if it is the quotient of hyperbolic plane, then it is cases was already known in Blumenthal's monograph. And the Riemann case is very easy because Riemann surface, the mapping is the group, the Fuchsian group is identity mapping. And then you just have to prove that on the Riemann sphere, on any sphere in the 3-dimensional space, 3 points can resolve and 2 points can't. 2 points can't because we saw the Riemannian bisector is the grace circle. On that grace circle, there are at least 2 points. Therefore, 2 points cannot resolve the Riemann sphere, and 3 points can, because if you just take one which is outside, well, if you take any 2 points and then take the grace circle, which is the Riemannian bisector, and then you take any point on that grace circle, then these 3 points will resolve the sphere. So proof of the Riemann surface case is actually complete, even with this demonstration for the hyperbolic case. Next natural question was, this second batch is about to be finished now. The next natural question was this question here, but in our joint paper with Professor Alan Bearden, he insisted on presenting one other problem instead of this one. I was actually quite adamant on presenting this question, but we did present a different question, which is something to do with Hilbert distance for a convex body in n-dimensional Euclidean space. And that question is still unresolved. But this question was not stated, but it was resolved by 2 Persian mathematicians immediately after our paper. So this is why people like us who teach all the time but don't have time to do research should not really present open problem. Then the open problem can be solved by someone else who is full-time researcher. For those two Iranian mathematicians are full-time researchers. The next natural question was continuing from the Riemann surface, that if X is an n-dimensional metric manifold, so this is not a differentiable manifold. This is no topological manifold. This is a dimensional metric manifold, a geometric manifold. Then is it true that it's a hyperbolic, it's a metric dimension is 1 greater than the Lebesgue dimension? This is the proper question. Now I'm about to retire, so I don't care. I published this problem, but this problem is not completely resolved yet. But the two Persian mathematicians resolved most of it. These are the two Persian mathematicians. They call the country now Iran. I don't like the name Iran. They are Persia. And then they did two papers immediately after our paper. First one is metric manifold, which is more or less resolved our question. Then they also did the XG manifold. And it is 1 greater than, as expected, 1 greater than the Lebesgue dimension. We did a few more theorems in that paper, and I'm not going to talk about it, but I will mention quickly because I'm using my third session for the second batch. I'm being late. I don't mind because going slow and understanding everything is better than going fast and covering a lot. This is a teaching philosophy. I'd rather have something which I master, so student can master instead of go, so far we did this, we did that. That is too much. I think it's not, I didn't do anything more anyway. So I'm happy that I don't say we did this, we did that. So that's fine. So here, things we did more is we completely determined topological spaces. No. Yes, topological spaces whose metric dimensions are 1. So, of course, Professor Ion Tomescu and Professor Muhammad Imran claimed that they also said that they determined all metric dimensions, all graphs with metric dimension 1. Of course, that is true, but we did determine all metric spaces of all topological spaces of metric dimension 1. That is one of the tiny results in this paper, but that result was not quite ideal, as I managed to discover later. But anyway, this is the result. But there is a nice thing there. Johnson and I recently proved such a result. Actually, Professor Muhammad Imran also and Tomescu also has examples that there are finite graphs whose metric dimension can be arbitrarily large. Of course, this statement is not true, but what they meant was for any given natural number n, there exists a finite simple connected graph whose metric dimension is equal to n. That is what they meant. They didn't mean any given finite graph has an arbitrarily large metric dimension. No, that is false. But anyway, this result, together with that result, which I have just displayed, theorem 5 here, should give somebody who is thinking a hint about something very strange here. So Johnson and I, Peter Johnson he's older than me. My collaborators are all older than me. Of Auburn University in Alabama, he and I considered this problem further and then found that we proved the result, but we haven't published it yet. But I'm going to tell it to you. Any finite simple connected graph can be given a metric. which is not the graph, the metric of the graph, but it is based on the metric of the graph, such that it has metric dimension 1. So we prove this. I challenge Professor Imran to recover our proof. But anyway, this is what we recently proved, that any finite simple connected graph can be given a metric distance function on it, which is based on the number of edges, of course, but its metric dimension under that metric is 1. So this actually agrees with the graph being one-dimensional topological space. Now, metric dimension is usually 1 bigger than the Lebesgue dimension, but in this case, it is actually 1. So let us stop here in this part. Any questions? I can start now so that I can go into part 3 because I'm working late, and I asked everybody to interrupt me, but nobody is interrupting me so far. I will stop this share and then I will share the third now. Can you all see the dimensions 3 vector groups? Just indicate to me. Yes, thank you. So this is now the vector group, because I have been announced vector groups, all that. The vector groups is now coming. This is the work by my PhD student, Yiming Lei. He's now in China in a very nice university. He immediately got a job after the PhD and left just when the COVID started, just after I was locked up. We were locked up since February of 2020. And then we started coming back to campus July of 2022. And he left sometime before June of 2020. So metric spaces of vector groups. These are Cayley graphs. These are Cayley graphs which become metric spaces using intrinsic graph metric. And we did several things. One of them is the isometric subspace of a metric space, having a larger dimension, which is known to many people. And as we have said already, that after our paper from that journal, 2 Persian mathematicians quickly made progresses further. I'm not going to talk about their results. Let them talk, because they are the experts. Of course, I refereed these papers. Now, concept of a Cayley graph is known to my audience. And now, but known to my audience mainly for finite groups. I'm not talking about the finite group. I'm talking about the group here, as I said. Let G be a group means it's a group. We didn't say it is a finite group. And let S be a generating set, which exists because every group has a generating set, even if it is infinite. Because if you take all the elements of the group, then it generates the group. Of course, you can now select smaller, and then you might find sometimes denumerably infinite, sometimes finite generating set, and so on. And generating set is required to satisfy the following 2 conditions. It's actually 3 conditions this set is satisfying. Number 1 is it generates the group. Number 2 is identity is not in it. Why? Because we're talking about, I give reasons all the time. We're talking about the distances in metric space. So having a loop, identity will give you a loop, but every vertex. Having a loop doesn't matter. It doesn't do anything to distances. Of course, every distance will be added finite number again and something like that. The loop doesn't loop, we delete. So that's why we don't have identity mapping in the generating set. And then it is closed under inverse taking. Why? Because we want to have the symmetry axiom for distances. Distance going from here to there must be equal to distance coming from there to here. This means that edges are not carrying, edges don't carry arrows, which means we edges are given by the generating set, elements of the generating set. So we require that the set is closed under inverse taking. Many people who use Cayley graphs, they don't explain why we use this. When the student asks, they stop. This is why we have these three conditions. Generating set means we're going to have connected graph. If it is not connected, then we consider component by component. So if we are talking about geometry, we talking about distances, then we want, this is very natural to require these three conditions. And then we can define a Cayley graph by assigning the vertex set. Our group is G, so we cannot use G for graph. Our graphs are metric spaces, so we use X. The graphs are not G, okay? G is group here. So vertex set is a graph. The group is infinite or even uncountably infinite. Then we have an uncountably infinitely many vertices, which cannot be counted, cannot be listed. And the edges are given by the generating set. So we say basically we're multiplying elements from this vertex. You multiply, take an element from the generating set, multiply from the right, and then that result is an edge going from here to there. And this is given by this way originally. This is a Cayley graph. And we have said this already. Now, X, Y be metric spaces, and with distant functions in each is a distant function. If there is a bijective mapping from one space to the other so that the distances are preserved, then we call this bijective mapping an isometry. When we are talking about subspaces, we need to talk about isometric subspace. If it is not an isometric subspace, then whatever you're talking about doesn't actually make too much sense. Our main references are these two. One is Blumenthal, the other one is Radcliffe 3 actually, and the other one is Gordon Royal's, Mackay-Royal's algebraic graphs. The isometries under composition of mappings form a group for every metric space. This is called group of isometries. Very natural. And if it is also a Cayley graph, then you have an automorphism group. It's given by this condition here. It's a bijective mapping so that images of edges are edges and images of non-edges are non-edges, which is written concisely as this, if and only if they. Now, automorphism, if the graph is a metric space also, now here our graphs are not finite, not necessarily finite. Finite is all included here because we didn't say the groups are finite. So our graphs can be finite or infinite. It doesn't, we didn't say anything. And here we have an automorphism group. We have an isometry group, as graph being a metric space. What is the relationship between the two groups? It's a very easy question, quizzing question. In our cases, they are identical, these two groups, which they actually verified as well. Now, we have another condition. We want our group to be torsion-free. It is abelian and torsion-free. We want to consider, and the metric groups, these groups are called vector groups. Torsion-free means that if there is an element with finite order, then that element is the identity element. So what we are saying is that if an element is not an identity element, then its order is not finite. Mathematicians nowadays, they really like negative definitions. They say that if an element is not identity, then its order is not finite. Instead of saying that, I should say that if an element has finite order, then it is the identity element. See, this is what they call contraposition. I don't like that word as I said already. So if it is a finite order, then its order is least positive, so that that power is equal to the identity element. And if a group has no torsion element other than no element of order, finite order other than the identity element, we call the group torsion-free. And the group is completely characterized by a reward-winning paper by Kurosh at the beginning of 20th century, published in Mathematische Annalen. He wrote in German, he's a Russian author. His group theory books, you should have it in your library. Volume 1, Volume 2, English translation. Now, if we have an abelian group, not necessarily finite, then we would like to use additive notation. So we don't want to say A times B, we want to say A plus B. And under additive notation, the identity element is called the zero element. And inverse element is called negative element. And torsion condition, now the two conditions of the generating set becomes zero is not in is, and it is closed under negative taking. And the torsion condition has become n times x is zero. So apart from the identity element, which you add the n times, it will become zero. There's no other element which satisfies this condition, which says this. And we consider this with good reasons. We don't actually say, like, well, we want to have this condition on it and without explanation. Then we define bisector. We defined it already a long time ago in the batch 1 or 2. Euclidean bisector. And now we'd like to consider this vector group. This vector group, which is n-fold Cartesian product of the ring of integers. And when n is equal to 2, this is called Gaussian integers. In this, we take the unit vectors. Let me ask a quiz question. How many unit vectors does this have? When I do this for my beginning linear algebra students, they usually cannot answer this question, which means they didn't really understand. If it is a real line, then there are 2 unit vectors. Let me just start from this simple case. 1 and -1. Their absolute value is equal to 1. 2 unit vectors on the real line. But as soon as you started having Cartesian plane, there are continuum many unit vectors on the unit circle, the circumference of the unit circle. The arrow is on the unit circle. And in this case, we have 2n unit vectors because this is a ring of integers. So when n is equal to 2, we have exactly 4 unit vectors. So the Cayley graph is going to be of degree 4. If we are taking unit vectors are such generating set, first of all. Secondly, 0 is definitely not a unit vector. 0 vector is not. Inverse of a unit vector is definitely a unit vector. So now we are talking about vector groups, so it's very easy to understand these now. So there are 2n unit vectors in this vector group. And we consider the Cayley graph, and this is the distance. And graph theorists are very good at using colorful descriptive words instead of definition, like this one. They call it Manhattan distance. I never use that phrase. My distance between x and 2 vectors x and y is sum of the absolute values of the differences. They call it Manhattan distance. Of course, you square each and then someone takes a square root, you get the Euclidean distance, right? And this graph, not only we, many people studied this before, but we have, first of all, established that monotonicity is true for isometric subspaces. Then we not only proved that this is not finitely resolvable, but Dr. Lei and I determined all bisectors in this. In fact, all bisectors for arbitrary n, at least 2, but for n equal to 1, something is very special going on there. And these are isometries, very special isometries. These are simply translations and rotations, but not any translation or any rotation in the general linear group or orthogonal group for R squared. On the orthogonal group of the Cartesian plane has many other translations and rotations. Our rotations and deflections are these coordinates of both integers. So these are, no rotation here, by the way. These are isometries, examples of isometries. You can easily prove. Using that isometry, we can reduce the general case down into, if you take any 2 points in the space, you take one of the points to be the origin, 0, 0, and the other point is in the first quadrant, if it is a Gaussian integers. And then, of course, isometries map bisectors to bisectors because bisectors is a geometric object defined through distances. Therefore, isometries preserve distances. Therefore, it's really metaphysical to understand that isometries map bisectors to bisectors. And then if 2 points, their distance in our space, our distances are not have not the same parity. Those two absolute values have not the same parity. Then the isometry, the bisector is empty. This is very easy to notice. And of course, this result can be also proved for graphs as well, finite graphs. Then we determine by isometries in this space, and we can show you the 2-dimensional case here. So if in this case, this distance from horizontal one is 1, 2, 3, 4, 5, and vertical one is 4, so 3. So they have the same parity. Same parity, the bisector looks like a straight, the Euclidean bisector, because Euclidean bisector is on the Euclidean plane is you take 2 points and then you use compass and ruler to find the bisector. It looks like Euclidean line, but if these two have the same parity, different parity, no, this, wait a minute. Oh no, if these two are not equal, because they have to have the same parity in order to, for the bisector to be non-empty. These two are not equal, and these two are equal, then it also looks like Euclidean bisector, but now you have 2 infinite quadrants filling the bisector. It's a subset of the bisector. This is what you can use to say that this is not finitely resolvable, finitely resolved. Just to show you that these are bisector points in the bisector. For example, this point, distance to the right red point is 1, 2, 3, 4. Distance to the left red point is 1, 2, 3, 4. That one, 1, 2, 3, 4, 4, 5, 6, 7, 8. That one, same. And here, if you want to see, if as soon as this point is included in the bisector, 1, 2, 3, 1, 2, 3, and then those points, they all have same distance to this point. Therefore, all those points are in the bisector. So this is about the idea of the proof, and I'm not going to bore you through this very detailed proof. This proof is complete here. Exactly what I said is written down here in this way. In three lemmas. Including the first lemma about the emptiness, whether the bisector is empty. The two lemmas preceding that cover these two cases. One is where the two absolute value of the distances of the components are equal. The other is they are not equal. And this statement, this theorem is true for any n at least 2. This is just the case for n equal to 2 here. You can easily see that this determination of these bisectors does not really depend on the dimension number being 2, but it depends on being at least 2. So this idea, which I just said here, it depends on being at least 2, n being at least 2. It doesn't depend on n being greater than 2 or any other, n being exactly equal. So this is our result. I think my time now, I need to leave you questions and we have some coffee. I'll do some. There's no electricity here for 2 hours, but if you are at least hearing me, I think my internet connection is alive. My computer can't stay on for 4 more hours, no problem. Thank you very much. Any questions?
I think this is a very wonderful idea for especially young students, that how we transform from an idea into mathematical proof, which just Professor Sheng Bau explained about this idea, and then all those is written in the form of proof, and these slides will be available to you. So Professor Sheng Bau, let's thank the speaker.
Thank you.